Well, it's a real pleasure to be here to speak in front of all my peers and a lot of friends and working associates I've known for many years, and an extra special pleasure since I actually had my son here today. I haven't spotted him in the audience. He's out there somewhere. I have my son here, and also my two senior partners, Frank Shirazi and longtime friend Frank Shirazi, and I think Robert Nance also. So it's an extra pleasure to be here speaking in front of all y'all today. The topic of this presentation, if it had been given 30 or 40 years ago, the topic would have been lessons learned. Unfortunately, being that it's 2017 and not 1985, the topic is lessons not being learned. And it involves having to do with all the extensive litigation that goes on nowadays. It seems like 90% of my time nowadays, and probably for the last 10 years, has been consulting on forensic investigations and working with lawyers on litigation, primarily defense of other engineering firms, defense of civil engineers, structural engineers, architects, that get sued frivolously because, frankly, of geotechnical issues that weren't identified. And so I thought this presentation might be particularly applicable since the topic of the CECon conference, I think next week, is going to be resiliency in engineering. Well, how much more resilient in engineering does it get by trying to stay in business by not being sued and having extensive legal defense claims and the domino effect related to insurance and that sort of thing. So, you know, the name of the game nowadays in this litigious nature, the times that we live in, is trying to stay out of trouble, trying to being sued frivolously or due to errors related to geotechnical engineering. And you know, the litigation is the largest amount of litigation nowadays involves expansive soils and geotechnical related issues, whether it be a geotechnical issue or a geotechnical consideration that wasn't considered by the design team, whether it be a structural engineer, architect, civil engineer, mechanical engineer. And it's interesting, but I think there was an attorney, Holly Fisk, gave a presentation to the technical group here about a year and a half ago. He's an attorney that I've worked with for years, and he primarily defends engineering firms, civil, structural, architectural. And you know, the topic of his presentation was he's been doing litigation for over 40 years, and over his 40-year career, he has always had at least 2 or 3 cases on his docket involving geotechnical issues and issues related to not predicting expansive soil behavior correctly on structures. So that was the topic of his presentation was, you know, try to stay out of trouble and lessen, and we geotechnical engineers need to try to figure this out because there's just way too many problems. And that's just one attorney. You know, there's 2 or 3 out there also that have just as many cases, and it's just it just seems to be out of control. And you say, well, you know, why are there so many lawsuits involving expansive soils? When, frankly, there's a lot of good geotech engineers out there across the state. It's not that there's not good geotech engineers out there. There are so many good ones out there. And so I'm not trying to say that the geotech community is not a good group of guys, a lot of smart guys out there. So, but there's a lot of issues relating to geotechnical engineering. A lot of the problems, a lot of them due to construction defects. When you know, construction defects are very unforgiving to expansive soils. And so if there is a construction defect and you're an expansive soil site, there will be problems. And of course, when there's problems, then everybody gets sued trying to sort it out. And but there are a lot of lawsuits out there regarding design issues related to expansive soils. And now there's been a lot of data developed over the years I'd say there's a lot of data, a lot of theoretical data, and a lot of data that's out there available to geotech engineers is really not applicable to the real world, to what really happens at some of these expansive soil sites. And a lot of these design parameters are not in line with actual geotechnical soil behavior. Not based on my theoretical knowledge, but based on my forensic experience, and see, what really happens at some of these sites compared to some of the recent data out there involving expansive soils. Now, like I said, the problem is when there's a problem on a construction site and it goes to litigation, everybody knows the old shotgun approach. Everybody gets involved, everybody gets sued, everybody has to defend themselves, and while they sort out, where's the problem. And if I was to ask for a hand to be raised for anybody that's ever been sued frivolously over a geotechnical issue, I'm sure the audience would have quite a large number of raised hands. So it's, like I said, geotechnical issues are not just related to, like I said, geotech engineers being named in a suit, but structural engineers, civil engineers, mechanical engineers, architects, general contractors. When there's a problem, all of us are going to be involved, and all of us are going to have to defend ourselves, and it's very frustrating. I know I've been in a lot of meetings with a lot of engineers, and they are so frustrated that they're having to defend themselves from a frivolous suit that not related to anything they did, but because they were victimized either by some construction defect or a improper geotechnical recommendation. And so I know it's frustrating for anybody to be involved in a litigation. Now, so I'll get into some of the meat of the problem. There was Texas Tech did a paper about 10 or 15 years, probably about 10 years ago, and they did a survey of geotech engineers across the state, asking them to, a very detailed survey on how do they predict their soil swell PVR calculations, and do they have confidence in their predictions and calculations, and it was amazing that most geotech engineers across the state still rely on the old TxDOT method of PVR determination. And any of you guys, civil engineers or structural engineers, architects, if you've ever gotten a geotech report and they talk about, geotech engineer talks about the swell prediction, they'll always reference typically they'll reference that TxDOT method, the Tex 124E method for soil swell determination. And so the bottom line of that survey by Texas Tech was most geotech engineers still use that method, but very few are comfortable that their calculations are correct, and they're not comfortable that those estimates are correct. Now, the thing is, when we use, the method has been used, or as I know, since I started my practice in 1974. It's been used because it's such an easy method to use. You just run an Atterberg limit, moisture content test. A technician that's been doing this work a couple months can do the testing to use this method, and it's such a simple method to use. But the thing is, when you go through the methodology, the assumptions made in that when that method was determined, it's not included in the actual methodology of going through the calculations. And I first got wind of this when I was actually talking with Dr. Litton on a project that we were working on together, and Dr. Litton at A&M, and we were talking about different things, and he mentioned, we were talking about things and asked me my opinions of certain things, and I said, well, if you're asking my opinion, that TxDOT method that was developed, and I thought he had developed the method. I said, that method is not realistic. When I do swell testing compared to that method is off by a factor of not a small margin, but 2 or 3. And he goes, well, I didn't develop that method. It was developed by somebody else. And he said the reason it's off by a factor of 2 or 3 was the assumption made in that method was that the swell restraint factor was only 0.33. In other words, they assumed that the swell is you know, soil swelling is three-dimensional. Swell pressures occur laterally, occur vertically, but the assumption made was that only 1/3 of the swell will occur vertically, and that 2/3 of the swell will occur laterally. And also, another comment on that method was I was talking about this topic a couple years ago, and I went on a technical committee, and an older gentleman raised his hand and said, I'm the classmate of Chester McDowell, who developed that method for TxDOT. He said, I was a classmate of Chester McDowell, and he said a long time ago that method should never be used for design of structures. And so there you go. So now, again, the method is very easy to use, and problems used to be a lot worse 20 or 30 years ago, especially when Las Colinas was developed, maybe 40 years ago. Some of these expansive soil sites, some of the original structures were designed using that TxDOT method. Our firm, back in those days, was actually John Haynes and Associates, with John Haynes and George Holland. Many of you older guys probably remember those guys. And John Haynes taught me when I came out of school that swell testing was the only accurate way to measure swell. And so, we were running swell tests and talking about how bad Las Colinas was, and how there was such a deep swell potential, deep-seated swell potential. There was really no way to control swell with deep-seated swell. And that Las Colinas, if you really got a structure, you're going to have to use piers and a crawl space out there because the swell is so bad. Well, we got blackballed. They have a list of Las Colinas Association had a list of geotech engineers who were on their approved list, and we were blackballed from doing any work out there. And so people, there were dozens of buildings that were built out there. And they were using the TxDOT method, and the thing about that TxDOT method is that, any site that you've got is magically tamed by putting in 3 or 4 foot of select fill when you use that method. You could have a 12-inch swell potential, but that method will tell you that if you put in 4 foot of select fill, your slab movements will be 1 inch. Well, I can't tell you how many lawsuits have been out there, and the old bathtub effect that we all know about nowadays. Nobody was aware of that, 30, 40 years ago. But, the bathtub effect occurred, and water getting the select fill, and then the slab would need 3 or 4 inches, and there'd be a lawsuit. So, that should have been a clue to everybody, that that TxDOT method is not reliable. Your method is telling you that you're going to have 1 inch of swell, and you end up getting 4 inches of swell within a relatively few years, and that really wasn't even the end of it. I don't know, some of these sites had a potential 6 or 8 inches of swell, when the report said it was going to be 1 inch. So grossly underestimated the swell factor using that method. And now the thing is, like I said, there's a lot of bad information out there. That TxDOT method, but again, it was developed for TxDOT. It's being used for commercial buildings. It's totally off because of that swell restraint factor of assuming only 1/3 of the swell is going to occur vertically. But there's a lot of other, there's been some recent studies out there where I see that people are doing swell testing and claiming the same silly claim that restraint factors of 0.3 to 0.5, indicating that there's going to be a lot of lateral expansion, and they may run swell tests and get an 8-inch swell potential, but say with a swell restraint factor 0.3 to 0.5, really we think it's only going to be 3 or 4 inches. I don't know how to be other than be direct, so the only thing I can, so I'm just going to be direct. That's absurd from a number of reasons. From a theoretical standpoint, I agree. Soil swelling is three-dimensional. Swell pressures will occur laterally, they'll occur vertically. But when you determine the amount, when you have a swelling soil on a free water source, the amount of pressure for the soil to swell laterally, the passive resistance of the soil of a hard, dry clay is probably 30 times the overburden pressure. So think about it, even from a theoretical standpoint. Is the soil going to swell laterally when the force that's required to push that soil laterally is 30 times the overburden pressure? When all it's got to do is, with the overburden pressure, it's just going to heave vertically, So your swell restraint factor is really close to 1, you're not going to get any significant lateral swell. It's just theoretically never made sense to me. But you know, people can argue theory. You know, I mean, we could spend all day talking theory, but you know, where the rubber meets the road is really what really happens in the real world. And I've been looking at these swell behaviors for over 40 years. And when I do a forensic investigation, I've always done borings and swell tests. I compared the amount of movement that occurred in a building in an area that didn't swell versus an area that did swell. And, you know, for example, a slab that heaves 6 inches, I'd do a boring there, determine that the soil was fairly saturated, there was less than an inch of heave remaining. I go to an area where there was no heave detected and do a boring and swell testing, and my swell results would show that, you know, the swell potential was 7 or 8 inches. And so it's always been a 1-to-1 correlation. The amount of heave that occurred plus the remaining swell has always been equal to the predicted swell in the similar dry condition that existed prior to construction. That's just forensic investigations. Again, you know, we used to do a lot of injection stabilization. We used to try to inject everything. Back 40 years ago when the method came out, lime slurry injection, water injection, we tried to inject everything because it was so economical to do. We learned when to predict how it doesn't always work, and we learned to predict when it works and when it doesn't work. But associated with the injection evaluations, again, this is hundreds of sites. I would always tell the contractor, look, you know, the soil is going to swell. So, you know, you're going to have to cut, after the swelling is finished, you're going to have to resurvey, cut the subgrade to remove the amount of swell. And because otherwise your select fill that you're putting down to cap that moisture condition injected soil is not going to be adequate. And so, you know, that was part of one of our checks was to make sure he did that. And so I'd always tell the contractor, you know, just so I, you know, for my own information, when you set grade stakes, you know, set your grade stakes, which is going to tell you how much swell you got to cut off to get back down to your select fill subgrade. Call me when you do that and tell me how much heave occurred, so I can compare the amount of heave that occurred during injection with my swell estimates. And of course, once you do an injection site, you know, you approve the injection site after you do borings and confirm that the swell has been reduced to less than an inch. So, without exception, every site that we've ever done, you know, the amount of heave, you know, the contractor would call me and go, I just can't believe that. You know, I had to cut off 8 inches of soil from that pad that swelled during the injection process. And without exception, the soil removed was always the same as the predicted soil swell PDR. So, you know, you can theorize or you can argue theory all you want, but, you know, where the rubber meets the road is the swell that's predicted with swell testing is 100% accurate. You know, there is no swell restraint factor. That's nonsense. The other thing, and well, you say, well, you know, I would think other geotech engineers would recognize that. And well, the other problem that we've got, you know, anytime there's a problem on a site or a problem with some design methodology, normally it's more than one issue that's related to a problem. So, and that's another reason why I think the geotech engineers, even though they use the TechStop method and they don't have any confidence in the method, they reported themselves they don't have any confidence in the method. It's not my opinion. It's reported on that survey. Well, it's the reason, you know, they do some swell testing, and their swell results would not indicate that TechStop method was grossly underestimating the swell. There's a reason for that too. Like I said, there's always a couple problems related to any serious problem. The reason being, when you're doing a swell test, technicians who do the swell testing try to use basically the same procedure as if you're doing a consolidation test. You're trimming a soil sample into a consolidation ring, and when you're doing a consolidation test on a moist, soft soil, that is so easy to trim a soil into that swell ring. You know, you can literally push the ring into the sample, and you get a very good contact with the soil in the test ring. But when you're trying to test an expansive soil that's friable and it's dry, it's jointed, and you're trying to get that dry, hard sample into a test ring, it's very crumbly in a dry condition, and you end up with voids around the test ring. And if you don't tamp soil in to fill those voids, what happens is when you start doing your swell test, the soil is just going to swell to fill the voids before it'll swell vertically, and it basically all the swell is dissipated. And and it's easy to prove. When I proved to myself that that was a problem was, I think it was back about 75, when I would be testing swell testing, and some soils would swell and some wouldn't, and I started looking at the unit weight and the moisture increase, and I saw that when I had a good swell result that I believed, the moisture increase was equal to the swell that I was predicting. When I didn't have a good result, when it didn't swell the way I thought it should, I looked at the unit weight, and the unit weight was grossly less than the actual unit weight of the soil. So I figured out pretty quickly that it's those voids around the ring that are causing the soil swell to not be reported properly. And so that's the other problem there, is that you've got to do the swell testing correctly to realize just how bad this swell potential is. And it's real easy to recognize a bad swell test. It's when your expansive clay, you look at your moisture increase during swell testing, and if your moisture increase is 10 or 12 percentage points and you're reporting a 1 or 2% swell, guess what? You got a bad result. So the swell, the increase in moisture content during testing will always equal your swell percentage. And when I look at a geotech report looking for problems, that's first thing I look at, and it's obvious what's happened. The other thing that's resulted in a lot of problems is design of soil swell uplift on piers. When I was Peck Hansen Thornburn, the design manual that I took when I was in school said that the swell uplift in a pier is a function of the shear strength of the soil. Shear strength of the soil adhering to the shaft. And for belled piers, the same manual said that the uplift resistance of a belled pier, it's not the conical shape. A lot of engineers think we have a belled pier and you do a conical shape of soil above the bell, thinking that that's what's going to resist uplift. The actual uplift resistance for belled piers is the soil directly above the bell, related to the bearing capacity of the soil directly above the bell. Now, I grant you, if you're designing a guy tower foundation, and you don't really care about some upward movement, but all you're trying to do is prevent the guy tower from falling over, and you're looking at the ultimate resistance of a belled pier, that conical method may be reasonable. But if you're designing a building foundation and you're trying to limit differential movements to less than a ½ inch, which what everybody wants, then when that belled pier heaves, it doesn't have to pull out of the ground to cause you a problem in litigation. All it has to do is heave 2 or 3 inches, and you're in a lawsuit. I can't tell you, I got 2 or 3 going on right now where that's happened, where the belled piers heave 2 or 3 inches, and now it's a major problem. And we're geotech engineers, where we goof up a little bit is, like I said, there's some bad information out there. If you were to do a test pier, drill pier, do an uplift test to determine, well, what's the adhesion on that pier shaft, for trying to determine, skin friction for a pier, or maybe even uplift resistance to a pier. Think about it. If you're drilling a pier into an undisturbed soil, the soil is just filling the pier hole for the most part, but there's no real lateral force on that soil, and there's also voids around the shaft. Kind of like if you ever looked at a column, structural column that was poured, and they didn't vibrate the concrete, and they used a slump of 3 or 4 inches and didn't vibrate the concrete. They pulled the forms, and you've got honeycombing, 30-40% honeycombing along a column. Well, that's kind of what you got when you got a drilled shaft in the ground. And some of this data that's been developed to determine adhesion of a shaft is based on that, adhesion of a soil of a drilled shaft. But think about it, that's not even remotely related to what happens at a site, for example, where you have an expansive soil site and you're using belled piers for support of a structurally suspended slab where there's been no moisture conditioning, and you've got a swell potential 6, 8, 10 inches, and you've got this extremely hard, dry, expansive clay. And then as that soil starts to swell, it's going to grab that pier. It's going to grab that pier and pull it up. And so the uplift on a pier that is swelling is much, much larger than the uplift the adhesion that you get if you just do a pier load uplift test on a pier that was just drilled into the ground. And like I said, a lot of these geotech reports, are reporting, soil swell uplift forces of 1,500, 2,000, when the shear strength is 5,000 or 6,000 PSF. I'm not saying you need to use 5,000 or 6,000 for uplift design, because you got to get into what really happens in the ground. Part of the pier will swell and soften while the remaining part will stay dry and hard. But bottom line is, a lot of this data that geotechs are using, it's not because they're bad engineers, is that they're using data that's not reliable. Like I'm saying, there's a lot of data out there that's not relevant to what's really happening out there. And you don't realize it until there's a doggone problem. So, bottom line is, if geotechnical engineers, like there's a lot of good ones out there, but these are the main problems, is that TxDOT method is useless, and there's no 0.33 restraint factor. That's what it's based on. You got to run your swell test correct and make sure that you're not getting an erroneous swell test by having all those voids around the ring. Structural engineers, if you get a report and you look at it and they got in the report that they used the TxDOT method, red flag. You look at the swell data, if you have a large increase in moisture and you don't have a large reported swell, red flag. Because again, structural engineers, they're getting sued for pier problems and have to defend themselves. Maybe at the end of the day, they find out that they're not the problem, but that's $100,000 later. And who wants to go through that? Excessive upward slab on grade movement. Again, if geotech misses it and the slab movements are over an inch, and structural engineer relied on that report, there's 2 or 3 inches of heave, structural engineers are getting sued. Civil engineers, you guys got to look at the geotech report and look at the swell that's possible, because there's also a lot of litigation regarding civil engineers where grades around the building are not adequate, where you end up with negative drainage and then ponding water conditions, and then flat work starts to drain towards the building, and then that becomes all kinds of issues. And then they look at the civil engineer and say, gee, your grading wasn't adequate to compensate for the amount of swell that was possible. A lot of civil engineers, I don't know if they even look at that, but if they do and they're looking at data that's swell potential is off by a factor of 2 or 3, your design's going to be compromised. Also, soil swell rebound under structures, below grade structures, whether it be pump stations, lift stations. If you're not looking at swell values correctly, you're going to get a lot of movement of the structures, of the piping connections to the structures. Widened roadways is another problem. If you're doing a widened roadway, you got an old 2-lane road, that's being widened to 4 to 6 lanes. The soil underneath that old narrow 2-lane road is moist and fully expanded into the widened area. It's expansive. You got all that potential for differential movement for the widened roadway section. There's been a lot of problems related to that. Mechanical engineers, if you're not looking at the swell beneath a structurally suspended slab, the preference is a crawl space. We put that in our reports, that if you're doing a structural floor, the preference is a suspended slab so that you can hang the utility lines to the suspended slab. But if you're using a void space, think about it. You're using a void space to protect the structure. What about those utility lines that are buried in the ground? And you've got a 6 or 8 inch swell potential for a utility line, and the utility line is rigidly connected to the structural slab. What's going to happen? The utility line is going to crush. You're going to have leaks. There's at least 3 or 4 lawsuits going on right now related to that issue, where mechanical engineers getting tagged by not doing the appropriate detailing. For number one, should have recommended a crawl space, but if they don't want to do that, there's other details out there for protecting utility lines from expansive soils, and mechanical engineers better be looking at that, because this is starting to become a hot topic for schools and hospitals and other buildings. Architects, you guys get tagged for everything. When there's a problem, the architect gets sued, and then then everybody's got to sort out who screwed up on his design team. A lot of times it's the architect wasn't really didn't serve as the quarterback that he really should have. The architect, he gets an expansive soil site, ought to make darn sure everybody understands that. Normally the structural engineer fully understands the nature of the expansive soils, but a lot of times the mechanical engineer, civil engineer, maybe they don't fully understand the implications of the expansive soil issues at the site. And the architect needs to say, hey man, we got an expansive soil site here. Here's the geotech report. Be sure to consider that in the design of your flat work near the building. General contractors, of course, a lot of times they are the problem. Construction flaws causing a problem. But a lot of times general contractors get tagged for frivolous details that maybe they didn't do just right, that they get tagged for a problem because you can always find something a contractor did wrong at a site. But a lot of times they get tagged for problems that they shouldn't get tagged for. Okay. Okie doke. Another one of the last issues, and the only reason I bring this up is it's gotten to be a ridiculous issue here, it seems recently. There's a law firm around now that they're targeting architects and engineers who've worked on school district projects. And their whole tactic is they go to a school district, within the before their 10-year warranty's up, and they offer to do a free inspection for the school district saying, hey, your 10-year warranty is going to be up. We'll do a free inspection for you, and if we find problems, then we'll help you get it fixed. Well, of course, they go in there, and there's I'm probably doing half a dozen schools in East Texas where the primary problem is moisture below the crawl space with a lot of humidity and mildew and different things. And of course, architects getting sued because of the moisture related to the expansive soils. You got clay soils. Water gets in there. If it's not drained properly, it's going to cause a mildew, corrosion issue. But when you go through the documents, just about every project it's been where construction guy, allowed water to accumulate in the crawl space during construction, didn't put in barriers that he was supposed to put in, get a lot of moisture accumulation in those crawl spaces, and then these poor architects get sued for huge lawsuit for they claim that they didn't do the ventilation properly, or the HVA system wasn't correct, or a whole laundry list of claims, when really it's frivolous claims related to the fact that you get moisture in that crawl space with expansive soils, it's not going to drain, so you better get the drainage issues right during construction as well as after construction, or else again it's something that's not paid attention to during construction, but then after construction, big issue. So I guess that's all I got. You got any time for questions?